Okay, please tell me when I should start, okay?
Sir, with the 5 minutes we will start, and
Okay,
nearly
okay.
50 participants have joined, so we will wait for another 5 minutes, then we will start.
Okay, thank you.
Would request all the participants to register with your name that is registered with ATAL ID at ATAL website. So, giving his file name and other names, it will be difficult for us to mark your attendance. So I would request all the participants register on MS Teams with registered name. So, Professor Datta?
Yes, sir.
I would like to start with your kind permission.
Yeah, please start.
So, good morning, all of you. It's a great pleasure and honor for me to introduce our session 4 speaker, Professor Ashish Datta, is Professor, Department of Mechanical Engineering, IIT Kanpur. He is research in humanoid robots for planning leg and hand skeletons, intelligent control, computer interface for rehabilitation robots. He is having administrative experience as head computer center IIT Kanpur, Dean coordinator for mechatronics IIT Kanpur. He is having member of the editorial board for the International Journal of Advanced Robotic Systems, International Journal for IEEE Sensors, and he was the member of various IEEE and associated journals. He has guided PhD thesis and so many MTech thesis, and he was awarded Japanese by the Japanese Ministry of Science and Technology Scholarship for Research in Japan in year 2002. So I request Professor Datta to start his presentation.
Okay, thank you. Yeah, thank you, sir, for the introduction. So I'll just stop the video because I think the bandwidth is having problem. So I will start
Yes, sir.
the screen sharing. Okay, I hope you can all see my screen now, right? Okay, so
Right,
today,
sir.
I'll be talking about Jacobian singularity and robot dynamics. And in the last couple of days, you have been introduced to forward kinematics, inverse kinematics, and we'll move on from there regarding Jacobian singularity and robot dynamics. Now, I'm a little old-fashioned in the sense that I will write down on the whiteboard. I will not use PPT. Okay, so in that sense, I'm a little old-fashioned. So let's start off first with Jacobian singularities and then with robot dynamics. Now, it would be better to have interaction, but I think it is not possible now, right, in this mode. So I'll start from here. Okay, so I'll just start off by writing. So first, you have studied a lot of things like forward kinematics, inverse kinematics. Now, if you look at how a robot actually works, so we have a base of a robot here, and there are links. Okay, so these are links. Now, how does the robot actually work? The robot at the joint level has what we call independent joint control. So there will be one motor. At the back of the motor, there will be a position sensor like an encoder, and in the front, there will be a gear. Okay. So each of these joints will be having one unit of this, and this is basically what we mean by independent joint control. So this structure is called independent joint control. Okay, joint control. Now, so how does the robot work? In your forward kinematics and inverse kinematics, suppose it is at this location and it wants to go to this location. How does it go there? So by doing inverse kinematics, there are different angles, which is theta 1, theta 2, theta 3. Okay. So by doing inverse kinematics in this location, it will find what is the corresponding position at this location. Okay. So it wants to go from here to here. So what it will do is at the joint, it will do for joint theta 1, position 1, theta 1 dash minus theta 1. Okay, and find out what is the error, okay, for theta 1. Then what the controller will do, whether it's a PD or a PID, it'll try and drive this error towards 0, which means that this joint theta 1 is moving from here to here. So that's how the controller works. And that is also the reason why you need to know inverse kinematics and forward kinematics. So at a given location, we are here. We want to go here. I will do inverse kinematics in both the positions, find out what is this corresponding joint angle to take it from here to here. Similarly, joint 2, there will be some corresponding angle, and joint 3 will have some angle. Okay, and the controller will make that angle equal to 0, the difference in the angle, and that is how it will reach the position 2. Now, this means that the controller is actually controlling the motor by giving some voltage input. So we are giving a voltage to the motor is rotating, and the rotation is going to the joint. The joint is moving, and then the end effector xy is changing. This is 2D, so I'm writing the xy. So which means that there are three things that are going on. If I talk in terms of space, one is you have voltage, which is going to the motor. Okay, so this is in volts. The motor is rotating. Motor rotates, what happens? The joint angle theta changes. Okay, so theta is changing at the joint level. Now, when the joint angle theta is changing, what is happening? The end effector xy is changing. Now, what is the units of this? This is degrees or radians. Okay, what is the unit of this? This is voltage. What is the unit of that xy? This is in meters per meters or centimeters. Okay, so there are basically three things which are happening. We are giving voltage to the motor is rotating, the joint is rotating because of that. And if the joint is rotating, then the end effector is rotating, end effector is moving. Now the end effector is moving in Cartesian space. Okay, this we know. The joint angle is moving in degrees, so this is polar. Okay, and the voltage is in voltage space. Now all these three spaces mathematically are different spaces. What it means is that if I give a voltage of 1 volt, it does not mean that the joint will move 1 degree. And if the joint moves 1 degree, it does not mean that the end effector will change by 1 meter. Okay, that means I am very much interested in knowing what is this mapping from one space to another space. And if I don't know this mapping, then I cannot actually control it. Why? because the end effector, what is desired is the end effector to follow a trajectory. Okay, so it has to go. So at every point in that trajectory, I need to find what is the corresponding joint angle and then control the joint angle to take it there. If I cannot do that, then there is no point in a robot. Right. So what is very important is to know this mapping. So from voltage space, what is the mapping there? Now, when I say mapping, is it many is to one? Is it 1:1? Is the mapping going nowhere? What do I mean by mapping going nowhere? For example, if I give an input at the joint, if I move the joint, the end effector moves. So this is the mapping. Now, if I move the joint by the same angle, the end effector moves in the same way. So this is a many is to one mapping now. Or if I give some joint angle motion, but the mapping does not, the end effector does not go anywhere. It is going off somewhere. It is not going in there at all. Okay, so this is my null space now. Okay, so the Jacobian, basically we want to find out what is the relation between the voltage that we are going to give to the motor, what is its effect on the joint angle, and if I move the joint angle, what is this effect on the end effector position. Why? Because at the end of the day, I want to move the end effector in a particular trajectory in the real world. Okay, so the user would say move the end effector with some in some file, maybe like this and like this. Okay, so what it means, it has to go to this point, it has to go to that point, then it has to go to that point, then it has to go to that point. And to do that, I need to know what is the relationship between the velocity input to the motor, to the joint angle, to the end effector motion. Okay. Now, it's interesting because you can do a task in many ways. So which way are you going to do the task? These questions have to be answered. Now, is there a task where you cannot go, where you cannot do? For example, there is a space here, just for example, where the robot end effector cannot go. Now, is there some space like that? Okay. Now, that point would be called a singularity. Now, all this is governed by what we call the Jacobian and the behavior of the Jacobian. Okay, so it's very, very important to understand how the Jacobian behaves in space, and that also will try and answer the question of what is energy optimal path. Okay, so this is my basic start off, that I want to find the relation between the motor voltage to the joint velocity to the end effector velocity. How can we do that? We take a very simple example. Okay, so I take a very, very simple example of a two-link system. So I take a two-link manipulator. Okay, two-link means XY only. So we have X axis and we have Y axis, which is two-link. And the manipulator is something like this. Okay. So this is theta1 and that's my theta2. This is L1, L2, and my end effector point is XY. Okay. So this is a very simple derivation. We have a two-link manipulator system where the joint angles are theta1, theta2, and the end effector is XY. I want to find the relation between the joint velocity and the end effector velocity. Why? Because I'm going to control the end effector velocity. So the user would say move the manipulator end effector or the gripper with a velocity of 1 meter per second in the X direction or Y direction. Okay. So I need to know what should be the corresponding joint velocity. Now, from geometry, we can very easily see that I can write two equations. What is the relation between xy and the joint velocity? So xy function of theta1, theta2. From geometry, we can see that, right? Now, if I write it in terms of geometry, what is x equal to? X is this distance. So that distance is x. What is it equal to? X is equal to L1, which is equal to L1. So this is L1 cos theta1, and this is that part is equal to L2 cos theta1 plus theta2. Okay, from geometry, it's very easy to determine this. So x is equal to L1 cos theta1. I'm writing in short C1 plus L2 cos theta1 plus theta2. This is what is x. So the x coordinate in terms of theta1 and theta2 is given by this equation. What about the y coordinate? Y coordinate is equal to how much is the y? Y is this distance. So it is this distance plus that distance, right? That is equal to y. So this distance is equal to L1 sine theta1, and that fellow is equal to L2 sine theta1 plus theta2. Okay. So cos 1, 2 means cos theta1 plus theta2. Okay. Similarly, sine 1, 2 means sine of theta1 plus theta2. Now, what is y equal to? Y is equal to L1 sine theta1 plus L2 sine theta1 plus theta2. Now, these two equations gives us the relation between the end effector position xy and the joint coordinates theta1 and theta2. L1, L2 are the link lengths. Now, what do I need to find? I need the velocity. So how do I get the velocity? I can differentiate this. So if I differentiate this, then I will get the relationship between the end effector velocity and the joint velocity, because I'm going to control the motor velocity, right? So at the control system, we control the motor velocities. So how do I do that? Now there are two variables, theta1 and theta2. So I'll differentiate this first with respect to theta1, then I'll differentiate with respect to theta2. Okay. Similarly, the second equation also, I will differentiate first with theta1, then with theta2. So if I write it like this, dx is equal to, I'm differentiating the first one, let's call this 1 and call this 2, with respect to theta1. Then I'm going to get L1 minus L1 sine theta1 minus L2 sine theta1 plus theta2. That is differentiating with respect to theta1. Then if I differentiate with respect to theta2, then the first term, this term does not have theta2, this term has theta2, so I'm going to get minus L2 sine theta1 plus theta2. Okay, so I'll write it in matrix form with respect to dx. Now with respect to dy, I'm going to get again, I'm differentiating the second fellow, so it is dy. You can say dx by dt, dy by dt. I'm writing it in short. So I differentiate with respect to theta1, so it is L1 cos theta1 plus L2 cos theta1 plus theta2. Then I differentiate equation 2 with respect to theta2, so it is L2 cos theta1 plus theta2. And here I'm going to write d theta1 and d theta2. Okay, so I've written it in matrix form. So this is one equation, the top one, dx is equal to that. So if you multiply it out, this is what you'll get in matrix form. Now, in short, I can write this as x bar is equal to j into theta dot. Okay. Now, you can take this as dx by dt. It's incremental velocity. This is not average velocity. This is incremental velocity. So I can similarly write dy by dt. And similarly, it is d theta 1 by dt again. Okay. So this matrix J, in this case it is 2 by 2, is called the Jacobian. So this matrix J is called the Jacobian matrix. What does the Jacobian matrix do? It gives a relation between the joint velocity and the end effector velocity, incremental velocity. Okay. So this matrix is very, very important in robotics because it governs the relation between the joint velocity and the end effector velocity. Now you can see that there are all funny terms signed in all combinations. Okay. I want to control the robot. Now, what we need to do is, I have x dot is equal to j into theta dot, in short. What the controller needs is theta dot, because I'm going to control the joint velocities, right? So theta dot is equal to j inverse of x dot. Okay. So I hope this derivative is clear. It's very, very simple. There is nothing complicated here. So this relationship gives us the relation between the joint velocity theta dot and the end effector velocity x dot, y dot, z dot, whatever. So the requirement is what? I will say I need to move my end effector with some velocity. So x dot is equal to 1 meter per second, for example, in the x direction or y direction. And I need to find what is the joint velocity. So the controller needs theta dot. And theta dot is at the controller level is equal to, now the inverse of the Jacobian is adjoint of the Jacobian, okay, divided by the determinant of Jacobian into x dot. I'm finding the inverse of x, j inverse. So my inverse of j is a square matrix here. It is adjoint of j by determinant of j is equal to the joint velocity. Okay. So this is a very, very important relationship. Now in this relationship, if you see that if determinant of j, okay, becomes equal to 0, what will happen to the joint velocity? Your joint velocity will become infinity. Okay, so this relationship is directly telling us that if the determinant of j becomes equal to 0, what will happen to the joint velocity? It will become infinity. Now, obviously, it's not possible because joint cannot get infinite velocity. Okay, it means infinite energy. That's not possible. And this point is what we call Biosingularity. Okay. So a singularity is a point where the joint velocity becomes infinity, which means in the physical world that the robot cannot go to that point. Why? Because to go to that point, it needs infinite energy. Now, you cannot get infinite energy, so obviously it cannot go to that point. So points where it cannot go are singular points, and this is the definition of singularity. Points where the robot cannot go. Okay. Now, it's more involved and it's more interesting in the sense that it also answers the question that if I have a robot manipulator, I am having a robot manipulator. Okay, let me take, so we are here. We have 3 degrees of freedom, and I'm here, and I want to go to this point. Okay, so this is the fixed space manipulator, 3 degrees of freedom, theta 1, theta 2, theta 3. I want to go from point 1 to point 2. How many ways are there of going? Okay. Now, because it is 3 degrees of freedom and just planar, okay, there would be infinite ways, which means I can go like this, 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 I can also try and go like this. Okay, so there are infinite ways of going. Now, if there are infinite ways of going, then which trajectory are you going to take? So this is a very valid question. That when you end up with infinite trajectories, you'll need to choose a trajectory which is energy optimal. Now, what do you mean by energy optimal? We see that this equation here, okay, can also tell us about the energy requirement. So for a particular velocity at the end effector, suppose this is 1 meter per second, okay, you can get different joint velocities you may end up with depending on the mapping. So which trajectory am I going to take? I will take a trajectory that will give me minimum energy. Okay, so if I want to go from point 1 to point 2, I take minimum energy trajectory. Now, from this equation 3, which is, what do you mean by minimum energy trajectory? It will basically mean if I maximize determinant of J, the energy requirement will get minimized. Okay, so from equation 3, we see that if I maximize J, okay, then my energy will get minimized. It is very clear from that equation. Okay, so and if I minimize determinant of J, make it go towards 0, then it goes towards the singularity point, which means my energy requirement is maximum now. Okay, so this very simple relationship actually tells us a lot of things. First of all, it defines singularity. These are points where the determinant of J becomes equal to 0. And it also tells us something about the energy requirement, that if you want to maximize, if you want to minimize energy, then you have to maximize J. Okay. So it tells us a lot of things. So if you're doing optimization and you're trying to find which trajectory the robot end effector should take, then the answer is very simple. You just maximize J. Okay, so find a trajectory where your Jacobian is going to get maximized, and that trajectory is going to give you minimum energy now. Okay, now what is J? We have seen that J is this one, this matrix. Okay, so please write down or remember this matrix. I will come to this very quickly. So this is a 2 by 2 matrix. Why 2 by 2? Because this is a 2 by 2 manipulator. If I have 3 degrees of freedom, what will happen? Okay, so your theta 1, theta 2, and theta 3 will come. Now, this relationship, equation 3, gives us the relationship between the singular position, and also it gives us a relation between minimizing energy. Now, this is very, very important because it's very interesting and very important, because if you think a little bit, we are also mechanisms. Okay, so we are also mechanisms. What do I mean? Is when you're picking up an object and you're keeping an object, imagine that on the table in front of you, there is a pen or something, you're picking it up and you're keeping it somewhere else. Okay, what trajectory are you going to follow? Now, you can have infinite trajectories, but if you observe, all human beings follow exactly the same trajectory when we are walking or when we are picking up an object and doing a task, which means that we are minimizing energy, or we have evolved in such a way that biological systems minimize energy when we are doing a task. And that is the reason why when we perform a task, we all perform in the same way. So I have to go one step further and prove that that is actually energy optimal. So here is an example. We have a robot manipulator, 2 degrees of freedom again, just for simplicity. Now, you know the workspace of this, the work volume, it will be something like this. Okay, it will be circular. I've just drawn half of it. So every point inside here, the robot manipulator can go. And in a 2 degree of freedom, manipulator, what is the singular positions? How do we find that? Similarly, just look at the Jacobian and then minimize it and find where it is becoming 0. So the Jacobian we found was equal to minus L1 sine 1. Jacobian I wrote just some time back, minus L2 sine 1 2, minus L2 sine 1 2, and at the bottom it was L1 cos 1 plus L2 cos 1 2, and here it is L2 cos 1 2. This was the Jacobian. Now, singularity is singular points. Sorry, singular points are where the determinant of J becomes 0. So what is the determinant of this? You know how to find the determinant of a 2 by 2 matrix. It is this into that minus that into that. Okay, so is this a 2 by 2 matrix? Now, if you multiply them out, something very interesting, that although cos signs are there, but all cancel out and you only get L1, L2 sine 2. This is interesting. You can multiply it out and see that all the sines and cos will cancel each other. And what you'll be left with is only L1, L2 sine 2. So it means that if you want to find that where the determinant is becoming 0, this should be equal to 0. That's a singular point for this two-link manipulator. Now we know L1, L2 sine 2, L1 and L2 cannot be, they are linked lengths, so they cannot become equal to 0. It's not possible, okay, because they are linked lengths. So the only possibility is sine 2 becoming 0. There's no other possibility. Now sine 2 will become 0 at what? At theta equal to 0 degrees and 180 degrees. Okay, so sine theta 2 becoming 0, and very interestingly, theta 1 is not in this equation. So this is theta 1, this is theta 2. So theta 1 doesn't appear anywhere in that equation, which means that it has no effect on singularity. It's only theta 2 which is there. And theta 2 equal to 0 degrees and 180 degrees means becoming this is my singular point. What are the singular points? They are exactly here. So if you can imagine it is stretched, this is theta 2 equal to 0. So the boundary is a singularity. This is a boundary singularity. And the other is when it is fully folded, and it is here. This is the other point. So there are 2 points, singular points. One point is on the boundary, which is all boundary points actually are boundary singularities. And the other fellow is there if L1 is equal to L2. Okay. If L1 is not equal to L2, then there'll be one region inside. But in this particular case, assuming L1 is equal to L2, okay, we have boundary singularity, and you have one singularity right at the end, right at that tip there. So we have found where the singular points are. In a 2 degree of freedom manipulator, there are no singular points inside the manipulator. That means there is no singularity inside the workspace. It is not there. But for a larger manipulator, 5 degree of freedom, 6 degree of freedom, you can actually find singular regions which are inside also. There could be singular regions which are inside. So this is giving us a direct answer as to what is the singular point for a 2 degree of freedom manipulator, and we have found it like this. Now we want to answer the other question, which is more important for us actually. Now why is this important? Is because if you think of a manipulator like this, again 2 degree of freedom, it has a workspace which is like this. Okay, where would question to the human? Okay, so if you can imagine yourself, okay, so this is our arm. Okay, this is our arm, right? So our arm is also L1, L2. So this is a 2 degree of freedom manipulator. This is L1, that is L2. Okay, so when you're picking up an object, okay, how would you pick up an object? I want to pick up an object from here and keep it there. I have infinite trajectories now. I can go from like this, I can go like this, I can go like this. Okay, so how do I answer this question? Now in the workspace, my workspace is very large. You know that human workspace will be like this. So anywhere you can do the task. Where would you do the task? Okay, there is no singular points inside that we have just seen. So the task is possible everywhere else. But where would you do? Would you do here? Would you do here? Would you do here? Would you do here? Where would you do? Okay, that's one question. The second question is, which trajectory would you take to do tasks? How do we answer that question? We are going to minimize energy. Okay, so we will do the task in a place where the energy is getting minimized. That is what we will do. So how do you minimize the energy, or how do you find minimum energy? We find it essentially by again looking at the determinant of J. So if I can maximize the determinant of J, then my energy will get minimized. That's a direct answer, right? So when we are doing any kind of optimization in robotics to find trajectories, we basically look at the Jacobian, and you can maximize it. If you maximize the Jacobian, the energy will get minimized automatically. Okay. So we have seen the determinant of J just in the previous slide is equal to L1, L2 sine 2. Again, very interesting. Theta 1 is nowhere in the picture. So theta 1 has no effect on energy actually. Wherever you are, theta 1 has nothing to do with it. It only depends on theta 2. And from this, if you want to maximize it, so maximum J would mean theta 2 is equal to 90 degrees or 270 degrees. 2 again is link length, so you can't do anything with that. So it basically means that for maximizing determinant of J, so max determinant J you get is this, and theta 2 is equal to 90 or 270 degrees. Okay. Now this is very interesting. Is it true, or this is just mathematics? Okay, very simple mathematics, but it's more important because a robot is going to live in the real world. Human beings also live in the real world. So is it true or is it not true, or it is just mathematics? Now if you think a little bit, where you're performing a task, if you see human beings, where in this workspace do we perform a task? So this is the human workspace. Okay, this is your hands, and you have a workspace. Where do you perform a task? Okay. So we'll perform a task somewhere in this region. Okay. Now in this region, this angle is 90 degrees. Please note, when you're writing on the desk, holding a pen and writing on a piece of paper, okay, your angle here, theta 2 angle, is 90 degrees or 270 degrees. Okay. Please note, so this one angle on this side is 90. Okay. Which indicates we have to write first, but we write in the minimizes the energy requirement of the hands. And this is a very, very important result. Now for the robot, where would the robot perform the task? The robot will perform the task somewhere in that region. So the arm will be like this and the arm will be like this. This angle is going to be 90. Okay, 90 or 270, whichever. Okay, so one condition is that, the other condition is this. They both mean the same thing. Okay, so one is 90, the other is 270. Okay, one is reverse of the other. So it's called elbow up and elbow down. So human beings also satisfy the condition because we are mechanisms in some way, and we always perform the task in this region. So please note the next time when you're eating, when you're writing, when you're picking up an object, it's only in this region in the workspace that we operate. We don't operate somewhere there or there or there. Okay, we don't. We can. It's inside the workspace, but we don't, because the energy requirement goes up. And if you go towards the outer boundary, you're going towards the singularity now, which means you require very high energy now. Okay, so we don't perform tasks on that region. For a robot also, it is exactly the same. Now this gives us two parameters. We looked at Jacobian and we looked at singularity, and we also in the process looked at minimizing trajectories to perform a task by minimizing energy. Now it is a little bit more involved in the sense that the Jacobian J also tells us about the direction of motion. What is the meaning of this Jacobian telling us about the direction of motion? It basically gives us a mapping between the theta dot at the joint level and the x dot at the end effector level. So this mapping is what we are interested in, and it is given by x dot is equal to j into theta dot. Okay, so this means that if I take the singular value decomposition of j, that means I'm going to take the j and break it up into two matrices. So if I do SVD, singular value decomposition, those of you who have studied principal component analysis or things like that, okay, where you take the singular value decomposition, we can break it up into two matrices with sigma u, sigma vt. Okay, this fellow is a diagonal matrix which consists of the singular value sigma 1 and sigma 2, okay, and u and vt are the basis vectors. Okay, this is the meaning of the taking SVD. Now if I take SVD of j, what would happen is I can get two directions in space. What this means is that this is a mapping. Okay, what this mapping is doing, it is rotating and it is and stretching. So what it means that if I give a unit, if I give an input of theta dot here, okay, is less than or equal to 1, then the output there is going to become an ellipsoid in a particular shape. Okay. What this basically means, this mapping, if I want to analyze how this mapping is behaving, I have to take the singular value decomposition of j, and this will give me the axis before rotation, and this fellow is the axis after rotation. Okay, so this is the axis after rotation. Okay, this is the meaning of mathematical meaning of this transformation. And sigma gives us two values, the singular values, sigma 1 and sigma 2. This gives me the major axis of the ellipse, and this gives me the minor axis of the ellipse. Okay. Now, what is this mapping doing? Okay. What this mapping is doing is, if the input theta dot is a unit sphere, theta dot is less than or equal to 1 is a unit sphere. Okay. What this is doing, this is my VT axis directions. Okay. Axis vector directions. What this mapping is doing is it is rotating it and translating. So an input sphere is getting shifted to an ellipsoid. Okay. And this is my major axis, sigma 1, this is my minor axis, sigma 2. And the axis directions are my u now. U and Vt are orthonormal matrices. Okay. So this is going one step ahead in looking at singularities and looking at the minimizing energy, but it is also giving us a direction in space in which you can move. Now, sigma 1 and sigma 2 is the direction in which you can move easily. Now, this is velocity. Remember, this is theta dot and this is x dot. So in the real world, they mean velocities. This means you can move in this direction very easily, but you cannot move in the other direction. You can move very easily in that direction. It's an ellipsoid, but you cannot move very easily in this direction. Okay. So as we are moving in space, what we see is that for the joint velocities which are given by a unit sphere, okay, so theta dot is less than or equal to 1 mod of that, the output is always going to be an ellipse, which means, let me come back here and make it a little bit more understanding in terms of the physical understanding. It basically means if I'm like this, okay, this is my, and that's my x dot. Okay, it basically means that for a given theta dot at the joint, the end effector velocity is going to be an ellipse like that. Okay. Now, for that ellipse, this fellow is going to become my theta 1, sigma 1, which is the maximum singular value, and this fellow is my sigma n, which is, or sigma 2 in this case, which is the minimum singular value, which means I can move very easily in that direction. Okay, but I cannot move in this direction. Move with difficulty. Now, this ellipse is going to change directions in the real world. So when this is coming closer, the ellipse starts off something like this. Okay, then it becomes like this. Then it becomes like this. It becomes in the center of the workspace. It becomes singular. Then it starts becoming ellipse again. Okay, then at the end of it, it becomes a straight line. So if I have a large, this manipulator figure is not correct. Let me draw it for a larger. Let me draw it like this. Okay. So for a larger manipulator, what we see is if my input velocities are contained in a unit sphere, the output at the end effector level is contained in an ellipsoid in three-dimensional space. And the major axis of the ellipse is the direction in which you can move. The minor axis is the direction in which it is difficult to move. And if it becomes a straight line, it basically means that you can move in that direction, but you cannot move in this direction because the minor axis is not there. It's a straight line. Okay. So this is what we get from the singular value decomposition of J. And this gives us a direction of moving in space. Now, singular value decomposition, why singular value? Because J, what I have explained, is a square matrix, but J can also be a non-square matrix. So this singular values, are basically square root of eigenvalues. Eigenvalues of J transpose. Okay, why JJ transpose? Because if if J is non-square, then a non-square matrix into its transpose will make it a square matrix. Then you can find, okay, and then we can take the square root of the eigenvalues, which is equal to the singular values. MATLAB has a direct command. It is called SVD. This is a MATLAB command. So if you say SVD of a matrix, it will tell you what is the singular values and what is that vectors U and V. We are more interested physically. Now, is this correct? Again, do we satisfy this? Now, this is very, very important because this is the direction in which you can move. A sphere means what? A sphere or a circle means that you can move in this direction, you can move in that direction, both equally. Okay, that means you can have equal velocity this side, equal velocity this side. Okay, and this is very important because if we are trying to control the robot, we need to know which direction you can move. Because if you're trying to move in a direction which is not possible, then you cannot get a velocity in that direction, although it is inside the work volume. Now, just one more small point before I move on to the next point, the next topic of dynamics. We won't go any more into this. It basically means that if you have your arm, okay, so suppose let me draw a human being here. So, well, it's not a robot. So our arm is like this. Okay, this is my upper arm. Okay, this is my upper arm. Okay. Now, when we are moving, this is a tooling system. So, at the near the body, when the arm is folded, your ellipse direction is something like this. Okay, our ellipse direction is like this. Okay, we can find that out. Then, as we are moving forward, it becomes like this. Then, the center of the workspace, it becomes a circle. Then it starts becoming ellipse again, and then finally towards the line. Okay, this is how it changes when we are moving like this. Okay, now what it means is that at the outer, when I'm fully stretching my arm, at this point, I have a velocity in this direction. I do not have a velocity component in that direction. Now you can stretch your arm and you can observe that when you're stretching your arm, if you want to move in this direction, you cannot. Okay, whereas you can move very easily in that direction. Okay. Why did that happen? Essentially, it happened because of this velocity change in the direction of the velocities of the ellipsoid, and that is again governed by your Jacobian. Okay. So this is something interesting to note, that the Jacobian, which we talked about for a two-link manipulator arm, which is very easy to derive. Okay, it tells you about singularity, the energy requirement of a task, how to find minimum energy trajectories, and it also tells you about manipulation ability. This term is called manipulation ability. So it's called manipulation ability. Okay, and the metric is determinant of, so this metric W is determinant of J. A square matrix, if it's a non-singular, it's a square matrix, and if it's a not square matrix, then it is square root of determinant of J transpose. So for a redundant manipulator, this is the manipulation ability. For a non-redundant system, it is that one. Okay. Now this W is a metric which will tell you that how good your manipulation ability index is. And if you note, it is again determinant of J. So if you are here, you can find out what is the value of J and then proceed. So again, in optimization, whether you perform a task, where would you perform a task? Would you perform here, here, or here? How would you answer that question? You simply look at the value of determinant of J. Okay. So if it is maximum, means your manipulation ability is maximum, which will come in this region. Okay. And this is an ellipse here. It's a straight line here, which means manipulation ability is very bad here and very bad here. So you should not do your task there. So for a large manipulator, this is one way of analyzing our task requirements. Go any more into this. We talked about Jacobian, singularity, manipulation ability, three things. Let's move on to dynamics now. Now, in terms of dynamics, so jump to the next topic of dynamics. Okay. Now we have a manipulator here, and it has multiple links. The base is fixed. Now at the end effector, there can be a force. Okay. Now at the joint level, we have joint position, we have joint velocity, and we have joint acceleration. Okay. Now when the manipulator is moving, going from one position to another position, there is some relationship between the joint velocities and the end effector velocity that we have seen in terms of the Jacobian. Now, something very funny happens here is that because this is a serial chain, okay, the velocities tend to propagate and forces also propagate. What does this mean? That if this link is moving, if let me call this 1, 2, 3, if link 1 is moving and link 2 and link 3 are not moving, okay, the velocities of link 1, the angular velocities, will start moving in that direction. So link 2 will have a velocity because link 1 is moving. Similarly, this velocity from here will go there, from here it will go there. Okay, so which basically means that your velocity and accelerations are propagating in that direction. Why? Because it is simply moving. In case of the human arm, exactly the same. Okay, suppose this is our arm, and you're moving your arm. Okay, so I'm moving my arm. Oh, sorry, I rubbed off the head. Okay, this is my arm. Okay, so I'm moving my arm. I'm moving this with a velocity theta 1 dot. Okay, now this arm, the second fellow is not moving. Theta 2 dot is equal to 0. It's not moving. But the joint actuator here for this joint will still need to give a force because this theta 1 dot, which is moving, Okay, will tend this theta1 dot will go in that direction, and this the link 2 will also have a velocity because the previous link is moving. Okay, so just because the link is not moving does not mean that it doesn't require a torque. Now, when when velocities and accelerations are moving in the forward direction, so velocities and accelerations move in the forward direction. What about forces? If there is a force which is acting there, okay, this is going to have an effect on this joint. It will have a reaction. Now, this forces reactions on this joint will have a reaction on this joint now. Now, the reactions on this joint will have a reaction this side now, and then it will have a reaction there. So, forces are moving in this direction. Okay. So, we see that velocities move in the forward direction and forces move in the reverse direction. Why this is a serial chain? Now, what are the kinds of forces and velocities that are there? So, the total torque is the sum of the inertia forces, inertia terms. Okay, so we know that this is the inertia term. Now, what are the other terms which are what are the other kinds of forces which are involved? Inertia is one. Then we have Coriolis plus centripetal. Why? Because this is rotating, right? So it will have Coriolis and centripetal. Plus there is gravity. Okay, so gravity is pulling it in this direction. That's G. Okay, so inertia, Coriolis, centripetal plus gravity. What about others? There is friction, and there can be external force. Okay, so external force F, which is acting at the end effector. So your total torque which is coming on your joint would be the sum of the inertia, because of the inertia torque, Coriolis and centripetal torque, plus gravity loading, gravity torque, plus friction, plus external forces. Okay, so my total dynamic equation has to find out each of these forces. Now, we know that the inertia forces depend on acceleration. Coriolis plus centripetal depend on position plus velocity. Gravity depends only on position, plus there are other forces, friction is there, plus external loading is there. Now the external forces again is J transpose into F, so the Jacobian comes in there again. Force is acting at the end effector F there can be converted into the joint torques by tau is equal to J into transpose into F, but this Jacobian here is in the last frame. Please note this, that this Jacobian is in the last frame. The Jacobian I derived in just a few slides back, so that is in 0 frame, the base frame. This fellow is in the last frame, whatever is the last frame. But you can convert them simply by using rotation matrices. So we need to find the inertia matrices. So if I say this is D, okay, then D into acceleration, plus H into velocity, this Coriolis centrifugal, plus G into gravity, plus friction, plus external forces, and so this is my total torque on the system. Okay. Now this is something that makes dynamic computation very difficult. Why? Because it is a function of theta, theta dot, theta double dot, and when the manipulator is moving, all of this is changing, and you cannot compute in real time. It's not possible. Okay. So how do we compute dynamics? So we are going to see 2 ways or 3 ways. Well, that is well, today we'll just look at 2 ways maybe. Okay. So the first method is by using Newton. First method can be the Lagrangian method. So Lagrange Euler method, we can call it Lagrangian formulation or Lagrange Euler, okay, method. Now this Lagrange Euler method is an energy method. Okay, so in the energy method, we are computing a Lagrangian L, which is the difference of the kinetic energy minus the potential energy. Then what we do is we put it in this equation d dt of dl by d theta dot minus dl by d theta is equal to my joint torques tau. Okay, so what we do is we find the kinetic energy of all the links, we find the potential energy of all the links, find a scalar function L, which is called the Lagrangian. Then I put it in this equation, and we find what is the torques acting at the joints. Now we know that in the case of a robot manipulator, there is a theta dot and there is a theta. Okay, these are generalized coordinates, but here it is theta. And we know that kinetic energy depends on theta dot, potential energy depends on theta. So I can simplify this equation, and I can write as dl. So if I simplify dl d by dt, what is L? L is equal to kinetic energy minus potential energy. It is differentiated with respect to theta dot, and theta dot only has kinetic energy. So I can write this as dk by d theta. Okay, this I can write it like that. This K stands for kinetic energy. Okay, minus dk by d theta plus du by d theta is equal to, okay. So what we have done is we have simplified this expression by observing that kinetic energy depends on the velocity, and potential energy depends on the position only. Okay, so by doing this, what we have done is we have tried to simplify our equation. Now, what about velocity propagation? Velocities also propagate from link to link. So there are two velocity. So this is one method, okay, called the Lagrangian Euler formulation. Now, what about Newton Euler? Now, a Newton Euler method basically will be determined by Newton's law. So we have the other method, which is Newton Euler. Okay. Now, in Newton Euler formulation, what we do is we compute theta dots as it goes along and accelerations as it goes forward. So from one link, it will have an effect on the other link, and in the next link and the next link, and will go like that in the forward direction. Okay, and the forces which are acting are going to come in the backward direction. So what we do is we see the propagation of velocity from link to link. Okay, and then what we find is at the CG of the links, what is the forces acting? Now forces are going to act because of Newton's law. Force is equal to mass into velocity. Okay, mass into acceleration, m into v into theta dot. This is not theta, it is v. Okay, so what we do is, because of this velocity and acceleration moving forward, there is going to be a force acting at these CGs of each of the joints, and these forces will propagate backwards now. So Newton Euler has two loops. One is the forward loop, where we compute the velocity forwards, where we compute the theta and the theta dots, okay, going forward. And then we have a backward loop, we call it the reverse loop, in which the forces come backwards. Okay, that means these accelerations are going to cause a force at the CG of the link, and those forces will come backwards and affect each. So we have a forward loop, and then we have a reverse loop in Newton Euler. Okay. So first, let's look at our Lagrangian Euler method, then we'll go on to Newton Euler. Now in Lagrange Euler method, let's look at a very simple example where we can look at a simple case, again two-link manipulator, because computing by hand is very difficult. Okay, so most of the time we are going to use a computer program, but we should know how to do it. So in the Lagrangian Euler formulation, we basically have to find the potential kinetic energy, and then we need to find the potential energy, find the Lagrangian, and then proceed. So let's look at Lagrangian Euler formulation. Okay. For a very simple system. So I'll take the example of a very, very simple. There is no point in showing for a 6 degree of freedom. I cannot do it by hand. And if I show a computer program, and it makes no sense. It's better to understand in 2 degrees of freedom, and then we can proceed. So this is a 2 degree of freedom manipulator, which has one revolute joint. There is one revolute joint, it's a revolute joint here, and there is a prismatic joint there. Okay, first understand how this moves. So this is a 2 degree of freedom example. One is a revolute joint, the first one, then there is a prismatic joint. Okay, so this is rotating joint, it is theta 1. Okay, it is a rotating joint. Now the second one is a prismatic joint, which can move front and back. Okay, so these are my two variables. Theta 1 here, and this fellow can move, that is theta 2. Okay, now there is a mass at the CG acting at the CG, so this is M1, and there is a mass which is at the CG again there, which is M2. So how does this manipulator move? First thing we need to understand, when it rotates, the joint 1 rotates. Okay, and joint 2 translates, it goes front and back. But if you note here, because joint 1 is rotating, okay, it will have, this rotation will have an effect on joint 2 also. Okay, that is making it clear that although joint 2 may not move, it will still have an effect because joint 1 is rotating now. Okay. Now, what is it that we need? We need x coordinate here. That's my y. Okay. Now, this is my link length L1. So let's call this link length L1 from there to there. And right from here to here, let me call it D2. From here to here, it is D2. So let's understand the problem first. This is a 2 degree of freedom manipulator. The first joint is revolute joint. Second joint is prismatic joint. It has 2 degrees of freedom. Now, when it rotates, the first one, theta 1, there'll be theta 1 and there'll be theta 1 dot. Okay. Now, what about link 2? When it is translating, there'll be D2. The change in the length D2 will change because it's linear translation, and it will become D2 dot. Okay. So the second link will has a linear velocity. The first one has a rotating velocity. So let's start off by writing our. So what else are we given? We are given the inertia of the links as IXX 1, 0, 0, 0, IYY 1, 0, 0, 0, and IZZ 1. Okay. And for the second fellow, it is IXX 2, 0, 0, 0, IXX 2, sorry, IYY. And this is 0, 0, IZZ 2. These are the inertias of the matter of the two links. Okay. So let's start off with the Lagrangian Euler formulation. What do we need to do? We need to find L, which is kinetic energy minus potential energy. So the first thing we need to do is to find the kinetic energy. So what is the kinetic energy of the first link? So K1 stands for kinetic energy of the first link is equal to half M1, okay, L1 dot squared, theta 1 dot squared, okay, plus half IZZ1 theta 1 dot squared. Let me explain this. This term here, okay, half m v squared. Okay, so this is half m v squared. Sorry, yeah. So this is my v squared. So half m v squared. V is equal to L1 into theta 1 dot. Okay. So because this fellow is rotating, so the linear velocity of that point is equal to L1 into theta 1 dot. V is equal to omega r, that we know, right? R is equal to L1 here, and omega is equal to theta 1 dot. Okay, so that's how I got my this term. So this is equal to my V, actually half m v squared. So half m v squared. Okay, that's how I got. Now the second term is half I ZZ1 theta 1 squared, theta 1 dot squared. Okay, so this is the kinetic energy of the first link. What is the kinetic energy of the second link? Which is equal to half of the second link translating, and it is also rotating because the rotation of the first link is there. So it will have two velocities. One is rotational velocity, okay, because of theta 1 dot, and it will have a translation velocity which is because of d2 dot. Okay, so this point here is having a rotational velocity plus it's having a translational velocity because the previous link was rotating. So the kinetic energy becomes equal to half m2, okay, v squared again, v2, this is my distance, v2 d2 squared into theta 1 dot squared plus d2 dot squared, okay, plus half I zz2 into theta 1 dot squared. So let me explain this. This part is the linear velocity. This part is because of the rotation of theta 1 dot. Okay, so which is actually half m v squared again. Now v is equal to d2 is the length into theta 1 dot is that. So from here. Okay. Now what about the next term? So it is half m2 d2 squared is the linear velocity. So when d2, so it will become d2 dot. Okay, it's translating. So it is half m v squared plus the other fellow half I zz2 into theta 1 dot squared. So this is my kinetic energy of 1, kinetic energy of 2. Now we need to find the potential energy. Now what is the potential energy of the first link? We know potential energy is equal to mg L into whatever is the link length L1. So this is my link theta 1. Okay, so this is moved by an angle theta 1. So what will be the potential energy of this point? It will be equal to m1 Okay, provided my reference is zero references here. Okay, this is my zero horizontal reference. So when we are taking the potential energy, our potential energy is going to become equal to U1 is equal to M1 L1G sine theta 1. Okay. Now, if we just go back here, because I took my reference to be here as my horizontal, this is actually not zero reference. Why? Because if I say this is my potential energy, when the actuator comes here, it feels it has reached the position and it will switch off the power. Okay. And then what will happen is this arm will just come down like that. So what I'm trying to say is that if you have a link like this, so this is one link just to give an example. If I say this is my zero reference, then if it comes here like this, it does not mean that there is no more potential energy. It has potential energy. Okay, so the actuator, if you switch it off, it will just come down like this. Similarly for our arm also. If you stretch your arm and you think that is zero reference, that is not zero reference because gravity is in this direction. And this is my zero reference. So we have to add what is called a gravity compensation. Okay, so this is my potential energy. Plus, because this is not zero reference, I have to add a gravity compensation, which is M1 L1 G, which means that even when it comes here, it requires the torque. How much torque? That much torque. M1 L1 G is still required. Okay, so this is my U1, which is the potential energy of the first link. The potential energy of the second link, U2, is equal to, let's go back. What is the potential energy? So it is this point, so it is being pulled like this. So there is a distance. Okay, D2 is there. Plus this will also have a gravity compensation. Okay, because this is not this horizontal axis is not the zero gravity axis. So theta U2 is equal to M2 G D2 sine theta 1. Okay, plus M2 G D2 max. Now here we are saying D2 max because D2 is a translational joint, so it can change. D2 is going to change, so the maximum length we take. Okay. So these two terms are very clear that when this is moving, theta 1 is changing, so this height is going to change. Okay. So it is equal to D2 into sine theta 1, and that is what I've written here. So I write my so we have K1 is the total kinetic energy is equal to K1 plus K2. Okay, that is my total kinetic energy, and the potential energy. Oh, sorry, I've written it as U. Okay, anyway, this is U is the potential energy. U is equal to U1 plus U2. Okay, so this I'm getting simply by adding. Next, I have to make my Lagrangian L. So Lagrangian L is equal to K minus U. Okay. All the terms are there, which I wrote down. So there is for kinetic energy it is these two, and for potential energy it is these two. So I'll do now to simplify it. What we said is that we are going to simplify this. So what we are going to do is, we are going to take. We are simplifying the equation, and what we are writing is the Lagrangian equation. I'm writing it as d by dt. I'm going to put it in this d by dt into dk by theta dot minus dk by d theta plus du by d theta is equal to my joint torque now. Okay. So I know what is k, I know what is u. All I need to do is just put in the values, and I can find what is tau. So if you do that a little bit, what we do get is we first compute this one, then we compute this one, then we compute that one. Okay. I know what is k and u. So dk by d theta dot is equal to, if we just go back, go back 2 pages, kinetic energy is a function of theta dot, right? So what we find is there is a theta dot here, there is a theta dot. Let me mark it here. There is a theta 1 dot here, there is a theta 1 dot there, then there is a d2 dot there, okay, and there is a theta 1 dot here. So kinetic energy has terms related to velocity, whereas potential energy does not have terms related to velocity. That is the way we wrote it like this. So now if I differentiate first with respect to theta 1 dot, then with respect to d2 dot, okay, that's what I'm doing. So if you do that, what we get is dk by d theta dot, get L1 squared plus izz IZZ1 plus IZZ2 plus M2 D2 squared into theta 1 dot. Okay. So the first equation I differentiated first with respect to theta 1 dot, okay, because that's the variable. Then I differentiate with respect to D2 dot. So if you differentiate with respect to D2 dot, we can find that D2 is only here. D2 dot is only here. Only this term is there. Okay, so this is the term for D2 dot. It's not there anywhere else. Okay, so what we do is, what term we get is M2 into D2 dot. Okay, so this is my dk by d theta dot. Then next we need to find dk by d theta. Sorry. Dk by d theta is equal to 0 m2 d2 into theta 1 dot square. Okay, so this is with respect to dk by d theta. Then I need du by d theta, which is equal to g into m1 plus m2 d2 L2 into cos theta 1. This is the first term. The second one is g m2 sine theta 2. Okay. So we have computed this one, then I compute this one, then I compute this one. Okay, I know what is k, I know what is u. And now we'll put them together. What I need to do is I need to do ddt of this again. So ddt of this one I need to do, so it is ddt of that. So what will essentially happen is theta 1 dot will become theta 1 double dot, and d2 dot will become d2 double dot. Now we need to see something, is that because there are two links, there is a coupling between the two links. What I mean is the effect of theta 1 dot will come on that fellow also. Okay, so which means that there is going to be a Coriolis kind of a force coming in now. So this link is moving, is having a velocity on a moving link, which is the previous link. So a Coriolis component is going to come now. Okay. So I'm going to differentiate with respect to theta 1 dot, then with respect to d2 dot, then with respect to theta 1 d2 dot and theta 1 dot. Sorry, yeah. So there is an interaction between these two fellows also. So what will happen is one term will come, which is my Coriolis term now. So now I take d by dt of this term. So here what we see is, because d2 is also a variable, theta 1 is also a variable, there will be an interaction between these two, and that is my Coriolis force. So when I'm taking d dt of this, I'll get one more term. So when I'm taking d dt of that, what we'll be getting is tau 1 is equal to m1 L1 squared plus IZZ1 plus IZZ plus M2 D2 squared theta 1 double dot. ddt of theta 1 dot is theta 1 double dot, plus because theta 1 is a variable and d2 is also a variable, I'm going to get a cross term, which is your Coriolis term, theta 1 dot, okay, plus m1 L1 plus m2 d2 into g cos theta 1. That's my torque 1. Torque 2 is equal to m2 d2 minus m2 d2 theta 1 dot squared plus m2g into sine theta 1. Okay, so this is my torque for the joint 1, and this is my torque for the joint 2. This is how we are deriving our two torques. The way it is written in a dynamic equation is torque is equal to mass into theta double dot plus, so m theta will be equal to, so we are writing it like this, plus v into theta theta dot plus g into theta. Okay, so I'm just going to rearrange the term. So we have an acceleration term here, we have a velocity term, which is here and here, and then we have just dependent on theta, which is there. So I can write this as mass is equal to, so in this equation it is equal to m1 L1 squared plus IZZ1 plus IZZ2 plus M2 D2 squared, and that is 0. This side is equal to 0, and that is M2 in matrix form. So it will become equal to theta 1 double dot into D2 double dot. Okay, so let me write this as tau. Okay, this is the first term, which is the inertia term, plus the second term, which is v theta theta dot, which is equal to 2m m2 d2 theta 1 dot d2 dot, and it is minus m2 d2 theta 1 dot squared. This is my second term, plus the gravity term, which is g, which is equal to m1 L1 plus m2. Sorry, there's no L1. Yeah, okay, L1 is the m1 L1 plus m2 d2 into g into cos theta 1 and m2g sine theta 1. Okay, so basically what we are getting is in the form of the dynamic equation. This is my inertia, this is Coriolis and centripetal. So this is Coriolis, sorry. So this is Coriolis plus centripetal, okay, and this is my gravity. Okay, so what we are seeing is in the equation of our dynamics, these are the three components: inertia component, then we have Coriolis centripetal components, then we have gravity components. Now this is my Coriolis force. So theta 1 dot and d2 dot, that is my Coriolis force, and centripetal force is theta 1 squared, theta 1 dot squared. Okay, so the dynamic equation comes out in this form, where we have inertia forces, Coriolis centripetal forces, and gravity forces. Now this is a very simple way of explaining, because by hand it's not possible to do more than 2 degrees of freedom. Okay, so for a real robot, you have to write a computer program in MATLAB, but the procedure is the same. Find kinetic energy, find potential energy, find the Lagrangian, and then proceed. Now the next, so this is one way of doing analysis. The advantage of this method is that the Lagrangian method is that it's an energy-based method. So all these terms you can see are matrices basically. Okay, and in MATLAB it is very easy to multiply matrices. So you can write this program in MATLAB and then perform this computation very, very easily. So this is the advantage of using the Lagrangian Euler. Now the other formulation is the Newton Euler, which is having the Newton Euler formulation, forward and backward recursion. So we can just have very briefly, let's look at that, and then we will stop. So very briefly, we can look at Newton Euler formulation. Now Newton Euler formulation, it is basically based on the velocities which are moving in the forward loop, and then the forces which are coming in the reverse loop. Okay. So when I mean by velocities moving in the forward loop, what it basically means is that if we have a link which is here, let me just draw this link, and we have another link which is forward loop. So this is another link which is on the forward loop. Okay, so let me call this axis Zi. You have studied DH parameters, so this is Zi and this is Zi plus 1. Okay, and there's an Xi. This is Xi and that is Xi plus 1. This is just an axis system. So it basically means that there is a velocity which is acting here, which is omega I, and the velocity on the other link is omega I plus 1, and there is a distance between them which is pi plus 1. Okay, so these are two links. If you can imagine in 3D, they have any shape. So because this link Zi is moving, it has an angular velocity of omega I. The next link will have, so what I'm trying to say is that this velocity will get, the velocity of link 2 will consist of velocity of the previous link plus its own velocity. So if I write it in matrix form, then omega I plus 1 is the angular velocity of I plus 1 at link, the next link, is equal to the rotation matrix I plus 1 I to I, velocity of the previous link plus its own velocity, which is theta 1 dot. Okay, so what this means is that the velocities propagate in that direction. Now, because it's moving, there will also be a component of linear velocity. Because it's rotating, it will have a component of linear velocity, and the linear velocity Vi plus 1 is equal to I plus 1 velocity of the previous link, that is Vi, plus omega I cross Pi plus 1. Okay, So this is the component that is coming because of the rotation of the previous link. Okay. So the velocity in the forward direction is vi plus 1, and then the next one is the linear velocity vi plus 1. So this is rotation, and this is translation velocity. So what we see is that the links are moving, and because of which the velocities are propagating in the forward direction. Now, what about forces? Now the forces will start propagating in the reverse direction. Okay. Now, suppose in the same figure we have a force now. Let me draw it in red. There is a force which is acting and a moment which is acting. Okay, let me draw it again. I'll quickly draw it again. Okay, so this is a link. This is my Zi, and this is Zi plus 1 axis. And there is a force which is acting here, which is my Fi, and it has a moment Ni. And the next link here has a force Fi plus 1 and a moment Ni plus 1. Okay, and there is a distance of Pi plus 1. Okay. Now, because there is a force of Fi plus 1 on the next link, this force will cause a force reaction and moment on the previous link now. So the forces are moving in this direction now. Okay. So the velocities move in the forward direction, forces move in the backward direction. Now, if I write my equation from equations of static equilibrium, then what we see is that we can write our force balance equation. So force balance Fi is equal to the rotation matrix I plus 1 into Fi plus 1. Okay. In the previous case, if you note, the rotation matrices were reversed. Please note here that the rotation matrix is reversed. Why? We are going from the ith frame to the I plus 1th frame. So it's the inverse of your rotation matrix, the matrix the way it is taught. Okay. Whereas in this case, we are coming backward in the correct direction. So it is I into I plus 1. So we are coming from here to here. So we are going from the I plus 1th, sorry, in the previous case, it was I to I plus 1. I plus 1 to I. It is I plus 1 to I frame. Okay. So from our equation of static equilibrium, sigma fx in all directions should be equal to 0 and sigma moment should be equal to 0. If you do that, Fi is equal to the rotation matrix into the next force. Okay, so we get one equation here. Now what about moments? Now the moments are equal to Ni. Ni is equal to the previous moment, Ri into I plus 1 into Ni plus 1 plus Pi plus 1 cross I plus 1 into Fi plus 1. Okay. So what is the moment acting at this point? It is the moment Ni, its own moment, plus the moment which is coming from the forward link, which is Ni plus 1. But this Ni plus 1 is in a different frame. So it is multiplied by Ri. It is being multiplied by Ri here. Okay. Because it's in a different frame. And the force is coming. Now, what is this Fi plus 1 doing? The Fi plus 1 is causing a moment now. So the effect of the moment on Fi link is equal to the moment of the next link, Ni plus 1, plus the moment being caused by this force, Ni plus 1, which is this one. Now, in this equation, we see that this is this part now, Ri plus 1 into Fi plus 1. So I can simplify it and write Ni is equal to R of I into I plus 1, Ni plus 1, plus Pi plus 1 cross Fi. Okay. So I'm simplifying this part. I'm putting this here and I'm simplifying it. So we have a force equation and we have moment equation. So by using these two equations, we can go in the forward direction and we can go in the reverse direction. And that is basically what we are doing for our Newtonian dynamics. Now these are vectors. Okay, so essentially in Newtonian Euler formulation, we are dealing with vectors. So we have to play with the so writing a program would mean dealing with vectors. So you can choose Newtonian Euler or you can choose Lagrangian Euler, and depending on which one is preferable to you in terms of writing a program, we can follow either one of them. Now, very briefly to talk about now, because these are vectors, okay, solving a problem will take a longer time. Okay, and you have to write a lot of more equations. Okay, but it can be done in a computer program much more easily. I'll just give a very brief solution of a problem so that you understand how dynamics is done. I solved a very simple problem. Now we can look at another very simple problem. Let us look at Newton Euler formulation. Okay, let's call it Newton Euler solution of this 2 degree of freedom system. We have one link here, another link here. Okay, so this is my theta 1, this is my theta 2, and this is my m1, this is m1, this is m2, like in the last. Now in this formulation, you see there is no gravity. Okay, so what we do is we have to introduce gravity. How do you introduce gravity? We simply say that there is a gravity force is in this direction, and say the acceleration due to gravity is acting in that direction. Okay, so if I do that, then we can solve this set of equations by two sets of equations. One is the outward direction. So this is my outward direction, which means there is a velocity theta 1 and theta 2 dots, and the effect of the velocities can be computed using the two equations, right? So I have omega 1 omega I plus 1 is equal to r of I plus 1 I into omega I plus theta I plus 1 theta dot into zi plus 1. Okay, that is one equation for the velocities in the forward direction. What about accelerations? If I differentiate that, I get omega I plus 1 dot is equal to r of I plus 1 I into omega 1 dot plus r into I plus 1 I into omega I cross theta I plus 1 dot plus theta double dot I plus 1. Okay, so this is my velocity, angular velocity. This is my angular acceleration. Similarly, I can find the angular velocity of the CG point, which is equal to I plus 1, which is equal to omega I plus 1 cross PC I plus 1 plus omega I plus 1 cross omega I plus 1 cross PC I plus 1 plus Vi plus 1 dot. Okay. Then I have to find what is the force. Now this is giving me the angular velocity and the angular acceleration as it going forward. Okay. Now what will be the effect of that? By using Newton's law, we can find out what is the effect. So it is going to cause a force at the CG, which is equal to mi plus 1 into Ci plus 1 dot, okay, which is mass into acceleration, and it will cause a moment, which is Ni plus 1, which is equal to I plus 1, that's the moment of inertia, into omega I plus 1 dot plus omega I plus 1 cross I plus 1 into omega I plus 1. Okay, so this is Newton and that is Euler. That's where the name Newton Euler comes from. Okay, so by doing this successively from link to link, we can go from one link to another link in the forward direction. Now what this is basically doing is it is telling me what is the forces acting on the CG of the links. So the forces are acting there. Now the forces acting there will cause a moment on the joints. Okay, and that in my reverse direction, the reverse recursion, I can find out what are the moments acting from these two equations. So by using these two equations, this equation and this equation, I can find out what are the joint torques, okay, which is this one. Okay, so in Newton Euler method, we go in two directions. One is the forward direction to find the effect of the joint velocity and accelerations on the CG of the links. Once we find the forces and moments acting there, we come backward and find what are the joint torques. Okay, now as you can see, these are all vectors. So it is a little bit more tiresome to write equations, but anyway, it depends on you which one you want to write. Okay, so this is very brief in trying to explain what is Jacobian singularity and also what is dynamics. Now, as you can see, that in the real case of a real robot, dynamics is not very easy. Okay, it's not a bit of program and it takes time to do all this. So what happens in terms of control? Okay, that is an important question. That in terms of control, what does dynamics of a system do? So we have a link. This part is very important. I'll just explain it a little bit and then I'll stop. Is we have an independent joint control, which is a motor, what is an encoder, which is a gear. and this is a voltage being given to the motor. Now, as far as the motor is considered or the controller is considered, it is independent joint control. It is only controlling that joint. It doesn't know what the other joints are doing. But as we have just seen that the dynamics is coupled. Okay. Now, what the other joints are doing, joints are disturbing it. Okay. So what the dynamics in a system does is it causes a disturbance in your system now. So this is a two-input system. So one input is your motor. The second input is the dynamic fellow coming as a disturbance. Okay. So this is what makes robot control very, very difficult. So dynamics coming as a disturbance. So essentially, if I draw in terms of control system, this plus minus, this is my theta desired. Okay, there is some controller. So this is my controller. But there is a second input which is coming from there, and this is my robot. And this is my feedback. We can say this is my sensor. Okay, this is coming back. So this is basically the control loop of a robot manipulator. And this is what my, this is plus plus. This is what my dynamic fellow is doing. So dynamic. Okay. So in reality, a robot control system is this one. It's a two-input system. Okay. But we'll simplify it and say it's a one-input system. Why? Because doing nonlinear control is more difficult. And you cannot compute this in real time. Okay. So computation of this in real time is not possible. Okay. So if you cannot compute in real time, you cannot estimate it also. So then there are estimators, there are intelligence systems, this and that. But linear control system essentially works, essentially because there is a gear ratio here, something to remember here. There is a gear. And the effect of this dynamic torque is reduced because of the gear, and because of which a linear control system works in controlling a robot manipulator. So a PD controller or a PID controller can control essentially because there is a gear ratio, okay, and which is reducing the dynamic torque tau d. Okay, that is the reason why a linear control system works reasonably well. But just understand that this is what dynamics does to a system. Okay, so I think I will stop here for the first part, and in the next part is going to be more presentation-based discussion on bipedal dynamics, bipedal locomotion. Okay, so I will stop presenting here. So if there are any questions, I can answer them, or we can break for tea. So if there are any questions, I can take them, or we will just break for tea.
Yes, Professor.
Yeah.
Hello.
Yeah, I can hear you.
Actually, we got very good information, and also the way you have explained, this methodology will become input for us how to take online classes also. And subject-wise, there is no doubt. It is very, very well explained, and we have learned how to handle the online class also. Thank you very much.
Okay, thank you.
Thank you.
Sir, I have a doubt.
Yeah, please.
Sir, if we are including the motor as well as a gearbox dynamics, like how do we find the dynamic equations if you include that also?
Oh, yes. So basically, if I can again, I'll have to come back and explain again. I'll just do that. Yeah. So basically, what is done is that you have a motor. So that's my motor. Okay. So this is my motor. There is a gearbox. That's my gearbox. And then on the other side, there is a link. So in terms of the structure, this is the structure of the robot controller. So there is a motor on one side. There is a link on the other side. Okay. Now, each of this has its own inertia and damping. Okay, so let me just write down the motor inertia is Jm and the damping is Bm. So this theta m is the motor velocity. There's a gearbox, there's a gear ratio of z, and on the other side we have theta L, which is the link velocity, and this is link inertia is, let's call it JL. Okay, and there is damping there, which is BL. Okay, so in the real world, this is the control system. Okay, for one motor, which is controlling a joint through a gear. Now, what are the gear ratio? Basically means JL is equal to the link, what the gear ratio does is it reduces the speed and increases the torque. Okay, so JL is equal to 1 by zeta Jm. Okay, so if I write my equation now, what will this equation be? So the motor is getting voltage, and what is that voltage doing? It is generating torque on the motor. The torque on the motor is rotating the gear, and the gear is rotating the link. That's how it's working. So the energy that is given to the motor is being consumed in causing the motor rotation, and that motor rotation is being consumed by the friction in the gearbox and in rotating the link on the other side. So if I write my equation, then it's Jm theta m double dot, okay, plus Bm double dot, right? Plus 1 by zeta, there is a gearbox there, plus JL, sorry, theta L double dot, okay, plus BL into theta dot is equal to tau m. Tau m is the motor torque. Okay, you can understand that, right? So now we have analyzed, we have written our equation of motion. Now if I convert it, okay, so Jm theta m double dot plus Bm, sorry, I wrote double dot there, is equal to theta m dot plus 1 by zeta. Now JL is equal to 1 by, sorry, this one is the other way around. So JL is equal to 1 by zeta theta m. Okay, so similarly this will become theta dot is equal to 1 by zeta theta m dot, and theta L double dot is equal to 1 by zeta into theta m double dot. Okay, so I'm going to reduce it to one equation, sorry, one variable. So there is a theta L, so I'm going to make it into theta m. So I'm going to use these three equations. So theta L dot is equal to 1 by zeta theta m dot. Okay, so if I do that, what will happen is theta m double dot by zeta plus BL into theta m dot by zeta is equal to tau m. Now if I take it out, what you'll notice is that if I'm going to take all these theta m dots together, okay, so I write it as theta m double dot plus Bm plus BL into theta m dot by zeta is equal to tau m, right? So now there is something very, very important and very, very interesting. And what is very important and very interesting here is that the gear ratio comes in the denominator. If you look at this equation, the gear ratio is coming here, 1 by zeta squared. Okay. Now what is JL? JL is the load torque. So theoretically, a PD control system or a linear control system should not work. Theoretically. Why? Because this fellow is there. Okay. So it means that if you're designing a PD controller or a PID controller, once you have tuned it, you have tuned the gains Kp and Kv. You have tuned it for that. But the moment the disturbance changes or the mass changes, the gain should not work anymore. And why will the mass change? Because the robot picks up something and the robot drops something. So the mass can change by a very large number. So why does it basically work is essentially because the disturbance is divided by zeta squared, which is the gear ratio. So if you have a gear ratio of say 100, that JL becomes JL by 10 raised to 4, which means that if I change it by 50 kg, your effect is actually very, very small. It is 0.005 only. Okay, so this is the reason why a linear control system works, because there is a gearbox. So if you, this is a very, very, very important point, that if you're trying to control the position of any system, you must have a gearbox in there. If you try and control without a gearbox, it basically means that in this equation, your zeta is equal to 1. So if there is any variation on JL, in a robotic system, there is going to be variation. Why? Because dynamics is there. Plus, the robot can pick up something and drop something. So it will become an uncontrolled system. Okay. So this is the way we actually model. And then you can look at, this is actually a spring mass damper. So you can look at stability of the system. And this is how it is modeled. Okay.
Yeah. Thank you. Thanks a lot, sir.
Anything else? Okay, then let's break for tea, and then I'll come back to biped locomotion after that. Okay.
Thank you, sir. Thanks for explaining such a nice way the Jacobian singularity and dynamics to our participants. Thank you so much, sir. And we will again join this session at 11:30, sir.
Okay. Thank you.
Thank you.